Welcome by Angular Compression, my part 2. Today we're going to be going in more depth in the angular compression, its mechanics and how it works, and just hopefully you'll have a better understanding on why we observe the things we do and how it happens. So let's get to it. Angular compression. These are the points. The larger angle is always the most predominant. Angles diminish on the vertical axis. Angles are always limited. All observations are optical, and thus the perception is always angular. Angles are dictated by variables such as optical phenomena, altitude, angle, and angle of incidence, as well as distance. The surface deck is always the largest angle to the observer's convergence point. Okay, let's start with point 1. The larger angle is always the most predominant. This is true. I mean, if you're gonna take, let's say you have two blocks next to each other, the one is larger than the other, and you put the one in front of the other, the larger block is going to block the smaller block, obviously, because the angular size is bigger. So the larger angle will always be the most predominant. The angles diminish on the vertical axis. This is what I meant with this is the vertical axis is you standing up and looking out into the distance. So the angle distance is you standing on the ground. The ground is obviously going to be the largest angle in the sky, but the ground is predominantly the largest angle to your observation. So the lower you're going in altitude, or the further the object you're observing, the angle will diminish vertically. So if you understand between your eyes and your feet to the deck, the surface, the further out it goes, or the lower you get, that angle is going to get smaller and smaller as the distance goes vertically. Angles are always limited. It's quite self-explanatory. I don't really need to explain that. You really can't see past a certain angle. If it's get to a certain point that the angle is so compressed, you wouldn't expect to see past it. All observations are optical, and thus the perception is always angular. Yes, it's also quite self-explanatory. You're looking optically, so you always got to take into consideration the things that you perceive is optical and not really physical. Yes, there's physical attributes to them, otherwise you wouldn't have optical illusions for it, but the angular relationships are always optical. Angles are dictated by variables such as optical phenomena, altitude, angle of incidence, and distance. Yes, this comes back to the angular phenomena such as miraging and refractions, and things you have to look through like smoke and mist and water vapors and so on. This all blocks your field of view. It makes it more difficult to see in the distance, and it helps to bring the diffraction limit sooner. I don't know how else I can explain this. Sorry. But this mixed in with your altitude and your angle of incidence really makes a difference to your distance. It all ties in together to change what you're observing and how you're observing it. The surface deck is always the largest angle to the observer's convergence points. The surface deck, that would be the surface floor that you're standing on. You can do the same thing, let's say taking it on a wall, doing sideways. At that point, your surface deck could be the side wall. So then your angles would not be diminishing vertically anymore, it would now be diminishing horizontal, but that's because your new surface deck is the wall. But if you're doing normal observations, standing on your feet and looking out, the surface deck would always be vertical to you. What did we just observe? We observed 6 panels of equal dimensions, showing the further panels diminishing into the closer panels here. The 2 closest panels could resolve the most out of the 6 panels. The masking tape markers also compressed into the larger angles. The angles adjacent to the axis that has the largest angle has observed angular compression. See, this is what I was talking with earlier. Your deck, this was the wall, the panel walls with the deck, surface deck, so and obviously that had the larger angle and everything compressed into that, including the masking tape, that you couldn't resolve it anymore, that it looked to become one large angle. So what happened is the closer larger angle of the wall compressed over the further smaller angle of the panels and the masking tape. Then you couldn't resolve the image anymore. That would be the diffraction limit appears to be more apparent at the furthest distance, which I just explained. The diffraction limit angle changes with altitude by the largest angle, and thus is affected most at lower altitude of the surface. This is what I was trying to explain. The diffraction limit is much more apparent the lower you are, as it makes it easier for the larger angle to compress over the smaller angle at that distance. So your resolution is going to be much more exaggerated. You're not going to be able to resolve easy, and that's where the diffraction limit comes in. Okay, this is just an orthographic representation of trying to explain what we've observed. Okay, let's see. It's the same statue, it's got the same angle, the same exact size, but the angular size would change with the distance. But because it's orthographic view, I wouldn't be able to change the actual angular size. Here, I'm just going to show you more or less on a rough why it would look to appear that the ground is compressing over the actual objects. The light due to the large angle hits your eye closer to you, and thus it has the bottom up abstraction effect this would be angular compression. Yes, if you see the blue triangle, that's the larger angle to the closest object. If you look at the red triangle to the furthest object, it's still the same object, it's just got a smaller angle. So what happens is the larger object would block the smaller object at the back, which is self-explanatory. Notice how the angle slopes to the furthest observation, giving a smaller angle to the deck. Yes. If you see where the observer is standing, his angle to the first object is a much larger angle to the angle to the furthest object. So that angle from the ground to his eyes has changed dramatically, and the slope is much more accentuated to the deck. This is just another rough trying to explain the same thing. The deck's angles are larger when closer to the observer. That's where you see the blue. That angle is larger than when it gets to red, and when it gets out even further to the green, it gets even smaller and smaller as it gets out. Again, since it's orthographic view, I have not changed the angular size, but if you do have the observation facing the object as a tree, it will get small in angular distance with distance. Vertical angles always change with distance. Okay, here's another representation where I try to do a perspective representation, trying to explain what is happening. This is the view from the observer looking into the distance. Now this would be a little grid on the ground going. As you can see, those ground angles are compressing as they get further into the distance. As you get more pixels to be compressed into that one small area in the distance is why it gives that perspective distance representation, because everything is converging into the convergence points. Let's visualize the close large angle deck compressing over the further smaller angle until it reaches the diffraction limit. Here we're going to be showing how it's just a visualization, how the larger angles just get smaller with distance as they compress and go to the convergence line. As you can see, I've colored them from green, yellow, orange, red and purple. You're more likely to see the compression of the angles more or less about the light orange, dark orange, red area. Then from there on, it should be just looking like one simple ordinary thing, and that's where you actually observe the object being obstructed bottom up. Here again, it's more just perspective, trying to show you, if you look at the paths everything in your field of view takes, it has a convergent that follows the bottom of obstruction with optical drop due to the angular compression and the barrel lines. If you look at just the clouds alone, they're at different levels, different vantage points, the trees, everything, the mountains. You can see the sun where it's sitting, it's actually sitting behind the cloud at the convergent points. So it's just following perspective. This I tried to illustrate from the top. It would be exactly what we were seeing from the last images with the bottom. You see the top larger angle gets smaller and smaller and smaller until it gets to the convergence point. That is the same reason why we're actually seeing the sunset. It's not because it's going behind any curve or anything, it's simply just due to perspective. It's moving out in the distance, and the larger angle of the deck, the surface of the earth, due to the distance with the sun, is compressing over the bottom of the sun until it finally moves away. The sun appears to set due to the optical drop. As it moves away, the sun converges into the diffraction limit, where the larger, closer angles have compressed over the further, smaller angled sun bottom up. Exactly what I just said. we see another example. You must always remember there are also topography on our plane, mountains and clouds and buildings that is closer and has larger angles to the deck, and thus you get sun rays under the clouds and behind mountains. You must always remember, in reality, even on a flat plane, which we still have topography, you still have mountains, you still have buildings, you still have distance to cover, you still have smoke to go through, and mist and water vapor and air and clouds and everything. This is why also the sunlight is also blocked at a distance, because it moves further away. The light can't travel and hit you anymore because it's just too far away. This is the same, just an example on a plane, how we would appear to see the sun set. It's exactly the same type of effect that you're seeing here. It's moving into the deck inside a plane, demonstrating how it appears for sunset in the distance as it goes to the convergence point where the objects are closer to you with a larger angle, and the deck compresses over the smaller angle. So you must remember there's people there sitting here, their heads are in the way, the seats are in the way, the perspective convergence point is in the way, and the larger angle of those people on the deck is compressing over that smaller angle of that light in the distance. Due to perspective, while it goes to convergence points, and this gives it the effect of it setting like the sun. And this is just an example of my boats over the horizon. Let's see a video as an example. This is exactly what I was talking about. If you see, the smaller boat is closer and it looks higher than the boat in the background. And same with this boat, but that's just because the angular size is larger because it's closer, and the deck angle is much larger. So the further away that ship is going, it has that effect that the hull is being compressed into the large angle of the deck of the sea. This is actually a perfect example of what I've been explaining all this time. Well, I just hope you have an open mind to understand what I've been saying, and thank you for watching. If you have any questions, feel free to ask. If you have any criticism, I'm more than happy to listen to it, and thank you for watching. Don't forget to like and subscribe, and just see that there's the horizon past that other boat, so that tells you something. And don't forget, you can see the miraging effects as well. Well, anyway, thank you for watching. Please don't forget to like, share and subscribe. God bless. Enjoy the rest of your day or evening, wherever you are.